Okay, this is a really quick limits review. Hey, the limit is the intended y value of a function. Limits can be added, subtracted, multiplied, divided, etc. Let's talk about evaluating a limit. The simplest way is to see if you can just substitute. So the limit of x approaches 5 of 18 minus x over x squared. If you simply substitute in, you get 18 minus 5 over 25. And that's your limit, direct substitution. What if, when you substitute, you get a 0 in the denominator? If I do direct substitution here, I get a limit that does not exist. 4 to the power of 3 is 64. 4 minus 4 is 0. This is a vertical asymptote. Therefore, the limit does not exist. Let's say we get 0 over 0 when we substitute in. Okay, if I substitute here, I have 9 minus 9 is 0. 3 minus 3 is 0. So I get 0 over 0. That's called indeterminate. But what it means is that you actually still have a limit. It means that this graph looks like this with a hole in it. So there is still a limit. We just have to find this y value right here. So to do that, one of the techniques we can use is factoring and canceling. So this equals the limit as x approaches 3. Look at my notation. X plus 3, x minus 3 is the factorization of the top. The x minus 3's cancel. So this limit equals this limit, even though they're different functions. And that means if I substitute in the 3 now, I get 3 plus 3 equals 6. And that is, in fact, the answer. This function does look like a line with a hole where y equals 6. So the limit is still 6 here as x approaches 3, even though the function never reaches that value. Another thing that might happen if you get 0 over 0 is it might be that you had a special trig limit. So I listed the special trig limits on your handout. But let's say you have one that's a little more interesting, such as sine 7x over 3x as x approaches 0. If I plug in sine of 0 is 0, 3 times 0 is 0. So that's 0 over 0. That means there is a limit here. I just have to find it. The graph doesn't exist here. There's a hole in it, right, or a discontinuity. But I can still find the limit. Because I know that the limit, I'll do it over here. The limit as x approaches 0 of sine u over u equals 1. If I can make this argument and the denominator match, then I'm going to be able to use this rule. So what I need is for my denominator to become 7x. To do that legally, I want 7x on the bottom, which means I'm going to need to multiply top and bottom by 7x. Now, what happens now is I can just rearrange. And I could say that this whole mess is equal to the limit as x approaches 0 of 7x over 3x times sine 7x over 7x. Same function as right here, just rearranged. These x's cancel. This becomes 7 over 3. I can use my special trig limit there, times 1. So my answer is 7 over 3 for this original limit. Doesn't quite always work out that way, so do make sure that you do the algebra involved when you do those. There's a new thing that we can try, and that's called L'Hopital's rule. So what you can do to shortcut finding a limit with that is to take the derivative of the numerator and the denominator. For example, if I have sine 5x over cos x minus 1 as x approaches 0, then I'm going to be in trouble because this is going to be 1 minus 1 and this is going to be 0. So we're going to have 0 over 0. The special trig limit doesn't work, but I can use that new thing we learned called L'Hopital's rule. And it says I can take the derivative of the numerator and the denominator and then try the limit. So how do I know this is going to work? Well, I'm not sure, but since I have 0 over 0, it's probably going to work. So I'm going to be careful to keep my limit notation. What is the derivative of sine 5x? That would be 5 cos 5x, because I have to use a chain rule. And then on the bottom, I would have negative sine x minus 1. So the derivative of cos is negative sine. So now, notice I'm not saying these two expressions are equal, but I'm saying their limits are equal. So now if I substitute, I'm going to have 5 times cos of 5 times 0, that's 5 times cos of 0, which is 1, over negative sine of 0, that's just 0, minus 1, which gives me an answer of negative 5. Notice that isn't a quotient rule, right? It's exactly what we told you not to do when we were learning the quotient rule. But the limits actually work if you take the derivative of the numerator, derivative of the denominator, and then plug in. Okay, if you want a limit just to exist, it can't be a vertical asymptote. So the limit as x approaches negative 7 of x plus 7 over x squared does not exist, because if I put negative 7 into this equation, I get 49 over 0. That's a vertical asymptote, does not exist. The limits from the left and the right have to agree. This is used in piecewise functions. So for example, if we do a piecewise function, let's do h of x equals 9 minus x squared, 14 minus 6x, x squared minus 20, and let's do x is less than 5, 5 is less than or equal to x is less than or equal to 8, so less than 8. X is greater than 8. Let's say we're supposed to find the limit as x approaches 5 of this function. We need to find out if the limit from the left and the right agree. So we want the limit as x approaches 5 from the left of h of x, and we want to see if that equals the limit as x approaches 5 from the right of h of x. So for the left is the negative side when x is less than 5. That would be 9 minus 5 squared, 9 minus 25 is negative 16. 14 minus 30, right, because 5 times 6, 14 minus 30 is also negative 16. So I can say that the limit as x approaches 5 of h of x equals negative 16. But I'd have to show my work, showing that it agreed from the left and the right. If I try it with 8, the limit of h of x as x approaches 8, we'll check 8 from the left and 8 from the right. 14 minus 48, that would be positive negative 34. And 64 minus 20 is positive 44. Those do not agree, therefore this limit does not exist. right? And that's because in this function, I'm not exactly sure what it looks like, but we would have, as we approach 8, we would have a negative linear, right? And this negative linear has a point right here of 8, negative 34. And then this quadratic has a point right there of 20, comma 44. So there is definitely not a limit there. Let's talk about limits approaching infinity. So on these, we're looking for horizontal asymptotes. So if I want to know, for example, the limit as x approaches infinity of 5x to the 7th minus 3x squared over 6x squared plus 7, then I use some logic. The top of this is going to always be growing faster than the bottom of this. The bigger exponent, the bigger degree is on top. As long as the bigger degree is on top, this thing's going to keep growing. It's just going to get bigger and bigger and bigger as x gets bigger. So it doesn't have a limit. So this limit does not exist. What if I have 10x minus 17 over 20x cubed minus 2x plus 8? In this case, the denominator is much bigger. So the denominator is going to keep getting bigger and bigger and bigger, and you're going to have these numerators that are proportionally much smaller, right? So this is going to get bigger. This is going to be much smaller. So my fraction is going to be getting tinier. That means that we're going to be going to 0, and that means that this is a horizontal asymptote at y equals 0. So the limit does exist. It's 0, and it means that whatever this function looks like as x gets really big, it has an asymptote as the function approaches 0. The other scenario is when you have equal degrees. So let's have 8x to the 10th over 9x to the 10th, and then it doesn't really matter what happens next. What matters here is that the degrees of these are the same. And as x gets bigger and bigger and bigger, the rest of this is barely going to matter, right? That's the 10th degree that's going to make the biggest difference. But this is 8 times something to the 10th degree, and this is 9 times something to the 10th degree. So this stops mattering, and in effect, these will kind of cancel out, which means our limit is going to actually be 8 over 9. And you can play with these in Desmos or something and graph them and see that they really do all work that way. Just a couple seconds left. So for continuity, we already talked about that a little bit with that piecewise. For something to be continuous, the limits from the left and the right must agree, even if the function value doesn't exist. So look at this case. Does the function value exist? Yes, f of 5 is, I don't know, we can call this 3. F of 5 equals 3. Does the limit exist? Yeah, the limit as x approaches 5 equals 7. The problem is that these two things don't agree. That's the third part of continuity. In this case, the limit as x approaches 5, which does not equal f of 5. The limit as x approaches 5 is 7, f of 5 is 3. This is not continuous by definition. Another way something can be not continuous is if you have a vertical asymptote. And another way can be simply if there's a break in the graph. Right? So here, the limit here would be 7. The limit here would be 5. So the limits from the left and the right don't agree here. So this also would not be continuous. All right, hopefully that was enough to get you rolling on your limits assignment.